What is quantum physics?
Quantum physics is a framework in which you can calculate dynamics for systems which obey the axioms of quantum mechanics, I guess. Like, yeah. So there's this thing called the wave function. The square of that amplitude of the wave function gives you the probability of a particle being at a place at a given time. There are certain things you can't measure to arbitrary precision at the same time.
Arbitrary precision?
Yeah,
What does
so
that
like
mean?
this is like the Heisenberg uncertainty principle is like I can't measure the position of something and the momentum of that same thing to better than some number. And that number is related to this thing called the Planck's constant. And so there are other variables that are like this, that are conjugate variables of each other, where you can only know so much about an object before you reach a limit.
And I'm trying to frame this question. You said there's only so much you can know an object before you reach a limit. And what is this limit exactly?
So, I mean, the example, like, so the Heisenberg uncertainty is this delta x, delta p, must be greater than h bar over 2. So on this side, this is how much you know about its position. That delta is just like the magnitude of how much you know about its position. This is how much you know about its momentum, so how much it's moving, how fast it is.
For those listening, the delta x
is your position uncertainty.
And delta p
is your momentum uncertainty. And then you have this h bar over here, which is just some number. So you know that this product of position and momentum uncertainties has to be larger than this number, h bar divided by 2.
Okay.
So this is one example of like this is the Heisenberg uncertainty principle in position and momentum space. Yeah. And this is not the case in classical physics. Like, I throw a ball, I can exactly calculate where the ball will be and how fast it will be going as a function of its trajectory. That's okay, that's allowed. In quantum physics, you can't do that. Yeah.
Okay.
I guess that's it. Yeah.
Okay. And how is quantum physics / mechanics discovered? Because this seems, because if it's outside the realm of classical physics, how does one actually kind of prove that it is real, or how did they do it back then?
Yeah. So you're now you're asking about the history, which honestly I'm not sure I'm the best. Well, I don't know for sure, but I think my understanding is it was a very like patchwork process where there were certain things that couldn't be explained, and then people had propositions, and then you could explain away some of those things, and blah blah blah. And there was this whole revolution of a bunch of people coming together as being like, what can you actually explain, right? So for example, you have something that is a hot object, right, and it emits a light. That's what glowing things, hot glowing things, look red. Hotter glowing things look white.
Mm-hmm.
Hotter than that, they go blue. So there's a transition in the wavelengths they emit. And there's this big moment in physics where people calculated what the spectrum of those wavelengths would look like. And if you try to use classical physics and don't quantize the light, you end up with a spectrum that diverges as you approach the ultraviolet. So as you go to shorter and shorter wavelengths, the number of photons you'd expect to emit shoots up. And this problem was called the UV catastrophe.
Catastrophe.
Yeah, because we couldn't explain why this behavior occurred, but we didn't see it happen in nature.
Right.
So one way you can solve this is if you say, okay, but I can only emit discrete packets of energy, and we call those packets photons, in this case, so particles of light, and you recalculate the spectrum based off that, you end up with something that looks like this, which is the actual, the black body spectrum. So if you have like an ideal thing that is glowing, its wavelength spectrum looks like this for a given temperature. And that's one side of it. The other side is you did particular experiments that showed that light is quantized, which is one of the experiments is called the photoelectric effect, which you shine light on a metal, and then you extract electrons from that metal, and it turns out that it doesn't depend on how bright your light source is, which is what you would expect if you thought of light as a wave, because the amplitude of that wave would be the corresponding to its energy. It mattered though what the wavelength of the light that you were shooting on the metal was. So short wavelengths, high energy. Higher energy kicked off electrons with more energy. But if I had a brighter source, I kicked off more electrons, but they would be at the same energy. So this showed us that photons themselves were like quantized pieces of light. So they could have any arbitrary energy, but they come in packets. That was another thing. The other thing is if you look at atomic spectra, so you have like a neon light, for example, you know that there are particular emission lines. And so Bohr started thinking about like, the Bohr model of the atom is you have this nucleus and you have like these shells of electrons, and when electrons transition between the shells, that's when you emit light of a specific frequency. And those are colors that you see in chemistry. So like there's many like different things, and I'm probably missing a bunch of stuff, but like there's many different kind of things that came about slowly over the early 1900s that led to the formulation of the kind of the standard formulation of quantum mechanics, which we now use daily.
That was such a cool explanation.
Yeah, I hope
I appreciate
I
it.
didn't screw it up for the viewers.